Hello, and welcome to this part of the FAST tutorial series. In today's video, we'll be looking at how to perform feature extraction on imaging datasets. So in today's video, we're going to be using the same dataset that we've been using in the last two videos. So this shows Pseudomonas aeruginosa moving over a surface using twitching motility, both in this bright field channel and in this channel in which YFP is expressed under a cyclic AMP sensitive promoter. And in the last video, segmentation, we saw how we could extract these different cells at each time point, generating a mask for every cell as a white object on a black background. So we have this list of images now showing where each cell is at every time point, and now we want to extract information about these cells over time. So we want to know, for example, where the cells are. We want to know how bright they're fluorescing, and we also want to know their morphological characteristics, so their length, their area, their orientation, etc. So to do that, we use this feature detection module in FAST. And as the name FAST suggests, so Feature Assisted Segmented Tracker, features are really an essential component of downstream elements of the pipeline. So not only are these features going to be useful in answering our hypothesis, which in this case is whether or not the brightness of YFP expression correlates with the speed of motion, but it's also going to be very useful in this tracking stage for allowing us to assign objects between time points. So to begin the feature extraction stage, we just click the feature button there, and this brings up a series of checkboxes that allow us to choose the features that we want to extract. We typically don't want to extract everything unless we absolutely have to. Just for time reasons, it's usually quicker to extract less information, but we can choose to turn on everything if we want. So I will be turning on all of these morphological characteristics, so length, area, width, and orientation. This centroid box is always ticked. That tells you the position of the objects at each time point. We can also choose in the two channels what we want to extract, so we can have the mean intensity in the two channels. So channel 1, this would tell us how bright the object is in the bright field channel, and this will tell us how bright it is in the fluorescence channel. And then we have the standard deviation checkboxes that allow us to determine the standard deviation of the pixel intensities within the mask of each object at each time point. So this would allow us to tell, for example, maybe if the fluorescence has localized to a specific point, because that will produce a high standard deviation instead of a lower standard deviation, which would be if it was fairly uniform throughout the cell. So I'm only really interested in the brightness of the YFP channel, which is channel 2, so I'll check that box and press make selection. And the final thing that we can choose is this morphology algorithm. This allows us to change the way that the shape of the objects is detected. So by default, this is set as ellipse fitting. This uses the entire boundary of the object and fits an ellipse to that boundary. It's very robust, provided that your object is relatively close to an ellipse shape. However, if that is not the case, if for example it's very long and skinny, it may tend to produce estimates that are too long or too narrow, for example. In these cases where your base object is not very close to an ellipse, it's usually better to use this perimeter distances option instead. That is less robust because it uses maxima within the distance is between pixels in your boundary, but it is better at assigning that distance if there's no other option available in the ellipse fitting. So with these options selected, I'm now going to press run them all. As before, we'll see this loading bar appear. That's just going to increase as we process through the entire dataset. And I have processed this already, so just to show you quickly what this gives us, we have this cell features.mat file that contains our cell feature information, and as you can see, this is around 200 to 300 times smaller than our original dataset. So this contains all of the salient information that we're going to be using during the tracking stage of the algorithm, and you can see it's very much compressed relative to the original imaging dataset. So that's going to give us a big speed advantage, both in terms of loading data and in terms of processing it. Okay, so in the next stage, we'll be performing tracking using this cell feature information, and we'll be discussing that in the next video. So see you there.